and we are going to discuss virtual work to find the displacement in different points of a beam, and then later we go to truss and frame. Again, this is a topic of interest in FE exam. Before we start with that, we are going to learn something about integration. Integral. You know the concept of integral from calculus. I'm not going to teach you again about that. We are going to learn a drawing method. Based on that drawing method, we find the result of integral. So it's a drawing method. And in that method, we are able to calculate the integral for some of the functions. And we need it for this chapter. And it has been proposed by Mr. Moore. Moore's method. The one that you learn in strength of material, statics, Moore circle, remember? The same person. So this is the summary of the method. We are going to evaluate an integral which is multiplication of two functions, fx and gx, from lower limit to upper limit, x1 and x2. So this is our target. So we have two functions. One of them is fx, the other one is gx. We are going to integrate it. There is a condition in Moore method, and it says that each of these functions has an order. For example, gx is a parabolic function, so the order is 2. So you remember it from calculus. If gx is a cubic function, then the order is 3. If gx is a line, the order of the function is 1. So each function has an order. It says that the sum of orders of fx and gx must be less than 3, or at most 3, is at most 3. So this is the condition. It means that fx could be a line, gx could be a line. So how much is the sum of the order? 1 plus 1, 2. If both of them are parabolic, then how much is the sum of the order? 2 plus 2 is 4. Then it means we cannot apply Moore method. So if one of them is parabolic, another one is a line, then the order is 3. It means it is applicable. This method with its condition is applicable for our discussion. And you can see the table is given in the textbook. So now we are going through this method to understand how those values in the table are derived. Yes?
Can the one be cubic if the other is 0?
The other is 0 means the other one is, yes, basically based on this definition. So if the other is 0, it means it is a constant function, which it means that the constant function it's a number, so the number come out, so it's easy to, okay. Now we can start it. This is the summary of the method. You have a function, so you can see we are just drawing it. It's based on drawing. So this is fx, and fx in terms of drawing is given from x1 to x2. Any question? The function is given based on the drawing. So basically, if I want to show you the function, this is fx. So in terms of drawing, we have fx. Now we go for gx. Based on the drawing, gx is something like this. So this is gx. From x1 to x2. So f and g are given. We are going to use Moore method to integrate f times g. So we are going to find this. The first step is finding the centroid of the top function. From statics, you know how to find the centroid for parabolic, for triangle, for rectangle, etc. For those triangle and rectangle, it's easy. For parabolic, there is a formula, but we don't need it. Later you will see. So you find the centroid, and then you just draw a vertical line. Okay, just come down. Once you draw this vertical line, you look at this ordinate of gx, and we show it with y bar. For the original first function, I mean for fx, there is an area under this function. We show it with am. So any questions so far? So you know the area under fx. Maybe fx is a triangle, maybe a rectangle, or even maybe a parabolic curve. So you are able to find the area using statics method. And once you find the centroid of this area, you just draw a vertical line, and then you find y bar. So the multiplication of these two, so integral from x1 to x2, fx times gx is am times y bar. This is the method. We are done. That is the method. So now we are going to apply this method for different figures as you saw in the table. Any question? So the first example. Integrate from 0 to 1 fx times gx using Mester-Moore method. So the first function is fx. It is given. This is the function. You can see it's a line, and these dimensions are just 1. So fx is given. It's a line. Gx is another line, but my drawing is not to the scale, but with different slope. So this is 2, this is 1. Okay, so we are going to apply Moore's method. What is the first step? We find the centroid of fx. So you know the centroid of the area of the triangle is 1/3, 2/3. So it's here. So this is 1/3. This is 2/3. Any question? What was your name? I forgot your name. So, what is the next step? Draw a vertical line from the centroid and this one is called y bar. How much is y bar? I'll give you time. Braden is good for this kind of question.
2/3.
It is 2/3 times this. 2/3 of
Oh,
this.
times 2, sorry, 4/3.
Yes. So he said 2/3 of this. And this is 2. So it means 2/3 of 2, which is 4/3. Did you get it? Okay. And Adrian, do you agree the area of this triangle is 1 times 1 divided by 2, which is 1/2?
Yes.
Now, look at this formula. The integral from 0 to 1, f g is am times y bar. Am is 1/2, y bar is 4/3. The answer is 2/3. So this was the drawing method. Yes.
If you were to flip g and x and find the area of g and the centroid of g, and then draw a line down to f, then would you get the same answer?
You have to get the same answer because integral f times g must be equal to integral g times f, right? So Reis is saying that if you just flip them, he said the location of this point, etc., will be changed. But remember, the area is also changed. This area is 2 times 1 divided by 2 is 1. So yes, you have to get the same answer. And you will get the same answer. Okay. The table, yes.
Why is y bar not 2/3?
This is 2/3 times 2. I appreciate your questions, Clement, but these are related to geometry of those kind of things. So, look at here. Let's say this is x, and this one is 2/3, 1/3. So it's just, I say 1/3, 2/3, the question mark. So now the question mark divided by x is 2/3, something like this, right?
So gx would be 2x, right? And then
Gx.
1/3 would be 1/3 times 2 to get y bar.
So, Braden, explain. This is 1/3, this is 2/3. Do you agree with this?
Yeah.
Okay. So now you just bring it down. Because this is 1 and this is 1, we have the same dimension, right?
Right.
Do you agree?
Yeah. Would the function for gx be 2x?
The function for gx, we don't have the function, we just have the drawing. And this is 2. And this is 1.
Okay.
Did you get it? Similar triangle. Oh, you can think about it. Let me write the details for you. Basically, this one is 2. Maybe because of this you are confused.
Okay, that's
maybe
why I
be-
initially said
yeah.
1/3 or 2/3.
Yeah, maybe because of this you are confused.
Yes.
So this is 2. So here we have 2.
Yeah,
Here
and then
we
1,
have.
okay.
Now, does it make sense now? Okay. So now it's.
Thank you.
So basically, this point is closer to the side, always. Yeah, okay. So now, we go to next example. So I'm going to erase this part. The question is asking to find integral, integrate from xa to xb, or to xd. And then f times G. Okay, using more method. Fx is given like this. This is A, B, C, D, PL, PL, LL. And then this is GX. GX is like this. Goes. My drawing is not to the scale. So this is 2L, A, B, C, D. Okay. And this is also 2L. So now you can see that we have A to B, we have B to C, we have C to D. So we break it down into 3 parts. We calculate it for AB, we calculate it for BC, and then CD. So basically, we are going to calculate the integral from A to B, Fx, Gx, and then from B to C, Fg, and then from C to D, Xc, Xd. So you know how to do it. When it comes only for AB, it means this is AB. You use the same method only for AB. And then you use the same method only for BC. It means you consider these two. And then repeat that method. And then you consider CD. And then repeat that method. And then eventually you just add them together. The same method. So we do it at the right side here. So I just quickly write it. So this is Fx, this is A, this is B, this is PL, the area is positive, and then AB, 2L, this is Gx. So from A to B, integral from A to B, F G is AM times Y bar, PL times L divided by 2, and 2L. So the final answer is PLQ. This is the first step. The second step, this is BC, this is PL, GX, BC is F, it is PL times L times L. AM Y bar, PL times L times L. The answer is PLQ. I do not go through the calculation of area, etc., because I think you can do it. The reason I don't go through it is because it takes time, so we have to cover many things. But so you know this is the area PL times L, PL times L, this is L. And that's it. So PL times L times the centroid, which is L. So I must give you a dimension. But the dimension is given here. Okay. So now we go for last one. Last one. This is F. This is CD. PL. And this is again L. So integral from C to D, FG is AM times Y bar, PL times L divided by 2 times negative 2 over L over 3. I write it in red color because this is negative. See, these are all positive, the areas are positive, but this one is negative. So Y bar is negative for this. Yes?
So far, the graphs that were given have consistent function based on like the segments. that we're
dimension.
looking at. So if there was like a difference in change of
You have to
function
break them down into
for
the
even
consistent.
further.
Yes.
So like if AB didn't, or sorry, if FX didn't line up with GX as nicely.
You have to break it down again.
Okay.
Yeah, but basically we don't have that complicated. Remember, we are learning this method for virtual work, right? So later when you apply this method to virtual work, basically what you need are just these. And remember the table in page 720? They are consistent in size because we just need them.
Okay.
We don't need more than that. But if they are not consistent, then you have to break them down. So, Clement, do you agree Y bar here is negative? That's why we write negative. So negative sign is important. So the final answer here, I write it in red, negative PL cube divided by 3. And now we add them together. We have PL cube, we have another PL cube, we have negative PL cube over 3. So we add them together. So I write it here. PL cube plus PL cube minus PL cube over 3. So the answer is 5 PL cube over 3. This is the final answer. And when you go to the table in page 720, it just gives you the tabulated formula based on this. You can use that table, but you basically don't understand what you are doing because you just follow the table. Okay. I'm going to erase this part. Only this part. You need more time to take note for this? No? Okay. Okay. Next example. Which is the last example for more method. Because basically this is what you need. The question is asking to evaluate integral is from A to C fx squared. The formula, the drawing is given. This is L, this is 2L, this is PL, and these are point A, B, and C. And basically this is the function fx. So how to solve it? What method do you recommend? Race.
You'd still use the, like, Moore's method and just draw f of x.
And yeah, so you just repeat fx. You just repeat, yeah. So we repeat fx, so it means that g is f again here. F times f. So I draw the first part. This is PL, this is L, A, B, and then I repeat it because it is f times f. And it is positive, so y bar is positive. So from here, AM times y bar, PL times L over 2, and so this is, just to make sure, this is y bar. How much should I write here, Clement? This, in my drawing is not this like this, right? 2/3 of L, 1/3 of L. This is the same. Do you agree? 2/3, 1/3. So, so this one is 2 over 3L, right? So now how much is y bar?
P2 over 3L.
Yes. 2 or 3 times PL, yes, the same. So 2 over 3 PL, and it is positive. Do you agree? It's positive. That's it. So the final answer is PL cube over 3. For the next part, I'm going to erase that. Second part of F is like this. BC. So this is F. This is PL and F. We just repeat PL, so AM times Y bar is PL times 2L over 2, because this is 2L. And Y bar is 2L over 2/3 of PL. And it is positive, so the final answer is 2 over 3 PL cube. So now we put them together. We have PL cube over 3, we have this one, so PL cube over 3, and 2 over 3 PL cube. So the final answer is just PL cube. That's it. So this was the Moore method. And we are done with this method. Yes?
What happens to the X? Is it still in there?
X, where, here?
For both of them.
X, what do you mean by X?
AMXY. Is X?
AMXY?
Well, it's multiplied. And then you're taking the area of the first one multiplied by the height of the second one based on the centrum.
Oh, it's
So it's-
area times the
Yes.
Y bar.
Yes.
Oh, I thought X was the.
Yeah, area times
variable.
volume.
No,
Okay, all right, okay. Any question? So basically this was the Moore method. And you have the table, so now you know it. Now we move to our concept, virtual work. We are in chapter 8, and we are going to use virtual work method. That is the concept. So the title is equation of virtual work. If you go to the textbook, you don't see this long equation. I'm going to write a long equation now. But don't panic, because we just use part of it. And the textbook doesn't show this long equation. But I have to show it to you so that you know what is going on in overall. So now you just write it. And then later I explain the components. You have this equation in the PDF file, in the link. Remember, you have the access to the sum of the part of the notes in PDF file from Brightspace. This one, you have it there. If you cannot read here, and then you don't need to memorize it, you can include in your clip sheet. So this is the complete equation for virtual work. You have it in the PDF file, but again, I read it. This is delta, the subscription is I. This is W, the subscription is R. This is M, this is M bar. EI, V, shear, V bar, G, AS. And N, N bar, T, T bar, GJ, N bar,
N.
alpha, yes.
The N bar is over what?
AE.
AE, okay.
E is modulus of elasticity. N bar, alpha delta T, M bar, alpha H, this is H. TB, TT, N bar eta, and R bar, K subscription delta, K subscription theta, M bar. Now, if you look at the textbook is just using this term. Basically, this equation tells us delta I is the amount of displacement of a point on your beam. Your beam is under different moment, different load, and you are looking for example, for point B. You want to know under this loading, arbitrary loading, how much is the displacement of point B? If you draw the deflection of your beam, something like this, you see point B moves down, right? This is deflection of the beam. You learned it in strength of material, deflection shape. This movement of point B from B to B prime is basically delta, displacement of point B. Do you agree? This delta is displacement of point B. So you are able to calculate the displacement of different points using this formula. Okay, so we know delta. So delta I is the displacement at a point. Yes?
So last two terms in that, what are they over?
We will get to them. So we go in this way. We go and then the explanation. So any question for this?
No.
So delta I is the displacement of any point. Could be point B or C, etc. That displacement could be vertical or sometimes horizontal. Remember, this formula is not only for the beam. This is for frame and truss as well. So point B could horizontally move. Not in this case, but in a frame. So the horizontal displacement of point B is also denoted by delta. So delta is showing the vertical or horizontal displacement of a point on your beam or frame or truss. WR is the support settlement. Sometimes due to human error, etc., you see the support moves down. It happens. And so this is the settlement of the support. Horizontal or vertical settlement of the support. It moves down horizontally or vertically. Okay. Now we are here. M is the equation of the bending moment over this beam. So you learned how to derive the equation of bending moment and shear force in statics and strength of material. If this is X, then you can derive the equation for bending moment. Remember bending moment diagram, shear force diagram? So M is actually a function of X. 2.2 times X squared, etc., or 2X cubed. So M is the equation. And later we will solve problems, so you will see what I mean. Now I'm just give you overall view. M bar is again the equation of the moment, but regardless of all of these loads. So you just remove all of these loads. What you have is just a beam alone, and then you apply a unit load right on point B. That is called virtual load. And then you find the equation for them. So we will practice it in next example. So now to just introduce these parameters, because Reis was asking, so V is the equation of the shear force, V bar is the equation of shear force when you apply a unit virtual load. G is the shear modulus of elasticity, AS is the effective area, N is normal force, N bar is the equation for normal force when you apply a unit virtual load, etc. T is torsional moment, so you know T bar is the same torsional moment when you apply unit load. Alpha is thermal expansion coefficient, delta T is the change of temperature. We don't use this term at all, but generally it is part of it. This is used for the gradient of temperature change. So, but we don't use it. So B stands for bottom, T stands for top. Again, we don't use this term. N bar is the equation for normal force when you apply virtual load. Eta is the displacement due to human error. These last two terms are used for spring. So if you have a linear spring or if you have a torsional spring. So So K is the constant value for linear spring. K, this is subscription. K subscription theta. K theta is the constant for the torsional spring. R is the load in your linear spring, could be tensile, could be compression. R bar is again the load in the linear spring, could be tension or tensile or compression when you apply a unit load. M is the torsional moment in your torsional moment spring. Okay, so you can see there are a lot of terms here, and I suggest you to wait after we solve a numerical example, and then if you have a question you can ask, because now of course you have a lot of questions. Again, we use this term in the textbook. So if you look at the textbook, this long equation is just shortened to this. So you just see delta on this. But later the textbook brings some of them in, and then you will be confused. So from the beginning you have to see the entire formula, and then we just use this, and sometimes we just use this. Now, raise question.
I still can't tell what the first subscript of K is.
Yeah, K delta. Yeah, okay. So now let's look at the first example and then we discuss this. And let me show you the textbook so you can see what's going on. We go back to article 7.3 is we have determined the vertical displacement of point B. Vertical displacement at point B, it means delta at point B vertically. And then this is the beam we have. We have a support here. We have a torsional spring. K subscription theta is EI over L. Point A, point B, we have a concentrated moment here shown by MO. The length of the beam is L, modulus of elasticity, and I, so EI is the rigidity. Okay. That is the question. We apply the method of virtual work before we get into the formula. So, because the effect of shear force and normal force are negligible, in most cases the question tells you that you only use the first term. Remember the textbook I showed you? The textbook is using only the first term because in most cases the effect of other terms is negligible. But sometimes it is not. So the question will tell you. In this case, we are just using effect of bending moment. So only consider effect of moment. Okay. The rest are negligible. So the question will tell you. And sometimes if you calculate the next terms, you will see that they are really negligible. So they affect the final answer like 1% or 2%. So we are just using the main equation, which is this one. Delta for point B vertically is integral mm over EI dx. Any questions so far? This is the formula. The question is telling us to only consider the effect of moment. But we also have the question from Race. We also have torsional spring, linear spring. So we don't have linear spring here, right? But we have a torsional spring. So we cannot ignore this term because we have the linear, the torsional spring plus this. So this is the formula now. Now, the first question is, what is M? M is the equation of bending moment for this beam. We go back to statics, we draw the bending moment, we derive the equation for M. This one is not the equation, it is the amount of moment inside the torsional spring under this loading. So any question for these two, so I highlight them with red. Any question? So you know how to find these. Of course we will find them later. The one that I highlighted in red are the moments under real loading. Okay. Real loading. Real loading is the real loading that you have in the question. Okay, so let's do it. I'm going to draw the bending moment diagram from statics. So test your knowledge from statics. This is beam. The diagram is this one. Okay, this is MO. Do you agree, Clement? This is the diagram for bending moment. In statics, you just used to cut it somewhere, if you remember, and then you use internal. If you don't remember, let me know, because I give you one more step, because I guess some of you still not remember. This is the method. We cut it here, Braden, and then you draw moment like this. Do you remember from statics? And then this is mx. And then you consider this free body diagram, and then you write sigma m is equal to 0 about this point, if I call it point O, for example. So let's do it. Sigma m about point O is 0 from statics. Then mx plus mo is 0. Mo is a parameter, for example, 10 Newton meter. It's a moment. So from here, the equation for mx is derived negative mo. And then that one is the drawing. Simple. Any question? So now we are done with one step. The next step, so do you agree we already found the equation for m? This is the equation for m, the one that we were looking for. And remember, MO is a parameter. So it could be given like a number, 10 Newton meter, 20 Newton meter. Now the second step is finding this red one. The amount, not the equation, the amount of moment inside the torsional spring.
You know, that definitely made their day.
So I just redraw this to the original shape. And from statics, you just simply know that when this is MO, then the moment inside this torsional moment is MO. Do you agree? Or if you just draw the free body diagram and then you write the equation. So let's go to the statics systematic method. This is MO, the systematic method. And then for the torsional spring, I show it with M. And then M is unknown. M is the amount of moment inside the torsional spring. I give you time to digest it. So do you agree with this free body diagram? Braden, is there any other load applied on this beam?
No.
Only these two. So now we write sigma m about point O, point A is 0. So from here, m, from here, negative m plus m is 0. So basically m is equal to mo. Let me check. I should assume this direction for the sign convention. Remember, the sign convention says this is positive according to the sign convention, and then positive, and then here negative. It has some tiny issues, so you have to be careful. We have to follow the sign convention. And we already discussed the sign convention for two right corner and left corner, right? So I'm following the sign convention for M, and then eventually it is negative MO. We already used this sign convention for inference line, if you remember. Do you remember, Clement, this one? Yes, anyone has? Just as a reminder, if this is a beam, internally this is the sign convention. I'm sure you understand it, for internal. But when it comes to the corner at A and B, you may still have some issues. So the sign convention for the corner is like this. And we already discussed. So you can memorize it or put it on your crib sheet for the corner. This was the concept in bending moment diagram, shear force diagram for the frame. So it means for the support at point A, this is the positive moment. For the support at point B, this is the positive moment.
So then for what you drew, wouldn't it still be positive M or minus MO? Because they're in the same direction.
So are you talking about here?
Yeah.
Okay, so I am following this one for
We're
A.
looking at A.
We are looking for point A because the torsional moment is at point A, right? If we don't have a torsional moment, then moment at point A is 0 because of this torsional moment. So I follow this sign convention for the torsional moment, and then we find it negative MO. So it means, for example, MO is 10 Newton meter, so this one is negative 10 Newton meter. So basically, when it is negative, it means I have to flip this sign. So I assume it to be in this direction based on the sign convention, but when the final answer is negative, it means I have to flip it. But I keep it in this way. This is the direction, and of course this is negative. So you can see there are some tiny issues. You can go back and review the shear force diagram bending moment. We are done with these two parts. So this was a reminder. We found these two red color. Any questions so far? We found these two red. And of course, EI is just EI, K theta is given. It could be a number. Okay, so the issue is these two red, and later these two in blue. We will find them. So I give you time to digest it before I move. Any question? Question? Okay, so now we go to these two. What is the meaning of bar here, Clem? When you put bar, it means it is virtual. So what? So it means this one is the equation of the bending moment in the same way, but forget about all these loadings. We just apply our own virtual load. Okay, and this is the same. This is the amount of moment in the torsional spring when we have virtual loading. So now, how to have the virtual loading? You need to draw your beam. Okay, this is the beam, so I have a support here. I have a torsional spring here. And that's it. So this is A, this is B. Do you agree? This is our beam without loading. Remove any load on the beam, whatever. Force, moment, whatever load you have, just remove them. So what you have is just the original beam. Then you need to apply a unit load. So apply virtual unit load. When we say virtual, it means it doesn't exist. We just assume. And it must be unit. So unit load is what? For example, 1 Newton, or 1 kilonewton, or 1 kip, or 1 pound. The unit load is 1, but it could be pound, etc. It doesn't matter. So I apply this 1 force, 1 Newton, for example, corresponding to the direction that we are actually looking for. So how shall I apply? So I will put, what is the target of this question? What is this question asking for?
Displacement of B.
Yes,
In terms of Y.
displacement at point B, horizontal or vertical?
Vertical.
Vertical. So I go to the same direction. Displacement at point B, vertical. If it was displacement at point B, horizontal, you have to draw your unit load horizontally. Why did I draw it downward? How do I know it is downward? In most cases, if you look at the textbook, it is downward, but it is up to you. You assume it downward. Eventually, when you calculate, you find delta By with its sign. If it is positive, it means delta By is downward. If it is negative, it means your assumption was wrong. The displacement is upward. Did you get it? Okay. So now, any question? Because this part is important. We apply a virtual load corresponding to the direction of displacement. Because this is vertical, down, this is vertical, so I draw it vertically. If it was delta Bx, then I have to draw it like this, horizontally. Okay, the rest is just, again, repeat what you have done here, repeat, but this time with this loading. Okay, I'm going to repeat that, but with new loading. Equation for mx. Okay, equation is, this is A, this is B, this is L, this is mx. You don't even need to find the equation for mx. You need to just draw it. So you don't need to find this. The drawing is enough. But for better understanding, I also write the equation for you. These are our statics. So mx is, if I just do this, and I have 1 minus x. And x, I assume X, for that one doesn't matter. I assume X is here. Again, you don't need to write the equation, but just for clarification. Remember, when you want to integrate, you just need the drawing. Remember Moore method? Moore method didn't give you the equation. It was just drawing. So as long as you have this drawing and this drawing, you're fine. But okay. Next step, we are going to find this. What is this? Clement, if you want to explain it. Is this the equation or the amount?
It's the same thing for unit load of, or how the spring's affected by unit load.
Mm-hmm.
one,
Yes,
right?
yeah. So how much is the amount of moment inside this spring?
It's equivalent to 1, or like 1 times the
Okay, so Clement is going to calculate it. Yes. Basically, this is the M bar. I put question mark, and then the length is L. Clement was explaining this. Sigma M about point, so I don't write it in this way. I just write the answer. So M is minus 1 times L, which is minus L. That's it. Do you agree, Clement? So, any question? So, you can see it is not difficult, but you have to be focused. If something goes wrong, then the whole solution jumble up. That's it. So we have the red color one, we have the blue one, just substitute them here. So I'm going to continue here. Or where should I? Because I don't want to erase it. So I continue here. Delta for B, Y is, oh, we need more space. So I have to erase the right side. So please take a note because I'm going to erase that part. We need more space. Anyone? I'm going to erase this part. Okay. I just write it because we don't have much time. So delta By is this one. This is Mx. This is M bar X. So from here, using Moore method, both of them are negative. So negative and negative will cancel each other. So the answer is mL squared over 2EI. So we are done with the first part using Moore method. And remember, both of them are negative, so they cancel each other. And so now I write the equation delta By is integral plus m negative this one also negative. So the final answer is this one. So basically I just substitute everything, nothing new. We have all of these values, I just substitute. That's it. Delta B is this one and it is positive. It means our assumption was correct. So B moves downward. If you have the length, if you have the modulus of elasticity, moment of inertia, you have the value for m, you can calculate delta B. For example, it is 2 mm. That's it.